Hello everyone, my name is Shuo, currently a master student at University of Science and Technology of China. This is a joint work with Huawei Noah's Ox Laboratory and the University of Adelaide. Here, I'm very glad to present it. In the practical application of autonomous driving, it's often faced with the replacement of various devices, such as vehicle upgrades, camera iterations, and so on. The performance of the originally trained model on the new device is unknown. Obviously, collecting more data on the new device is a safe solution, but it's not always economical. We first explore the performance gap of different devices on multi-view 3D detection. NewSense and Waymo are two popular benchmarks for 3D detection, and their data collection devices are not identical. We train a detector based on NewSense and then apply it directly to Waymo. We can find that the ground truth and detected results have obvious location bias. We analyze the reasons from the perspective of probability. The learning process can be considered as learning the joint probability distribution of y, x, k, and e, where y is the ground truth, x is the image representations, k is the intrinsic parameters, and e is the extrinsic parameters. According to Bayes' formula, we decompose the joint distribution. Here, the joint probability distribution of x, k, and e is a mapping that projects a perspective image into the feature map in bird-eye view, and the conditional probability represents the detection height. Similar to the domain gap in 2D detection, we make the covariate shift assumption for the conditional probability, then treat data from different sources as different domains. When there's no domain gap, it means that p source is equal to p target. Therefore, the domain gap only comes from the conversion process from perspective view to bird-eye view, which is composed of depth estimation and image representation. Based on this, we introduce our method. Two cameras O1 and O2 with various intrinsic parameters shoot the same object at the same distance. The imaging size of the object can be quite different, just as the size of the right parts in A and B. This indicates that the estimated depth has been entangled with the intrinsic parameters of the camera. We can first acquire the original pixel size S, then we set a constant C representing the pixel size as a given reference focal length. Based on this, we can acquire the scale environment depth, which dm is the metric depth. As noted in camera pose methods, monocular depth predictors are naturally biased to the distribution of camera poses. So we utilize the homography to generate various perspective images. Concurrently, we first perturb the camera poses, then obtain the LiDAR to camera transformation matrix before and after the disturbance, and project the points at the bottom center of the ground truth onto the two images using the above two transformation matrix. When there are more than 4 pairs of matching points, we can restore the homography matrix, and then perform perspective transformation on the entire image. The right part is the implementation details. Using the gradient reverse layer to obtain domain-agnostic features has been widely used in domain adaptation tasks, but we have no access to the target domain. So we quantize the focal length interval of the source domain into k subintervals. Each subinterval represents a domain, so we construct some pseudodomains and then obtain the domain-agnostic feature. This is the overall architecture. We validate our methods through 4 different experimental settings. For example, we regard NewSense as a source domain and Waymo as a target domain. Our method can greatly improve the generalization ability of the source domain and retrieve 64% of the oracle performance without compromising the performance of the source domain. On the other three settings, our method also greatly alleviates the domain gap. Here are some simple visualizations. Our method can effectively solve the position deviation. Thank you for watching this video.